Michael, good to see you. You made the trip. Today, we're pulling back the curtain on the supplement industry. The fillers, the excipients, the toxins, storage issues. We're gonna learn so much from you today, Michael. I can't wait. I mean, look at this. We're in Helaina Labs. We're gonna learn all about the truth about the supplement industry.
So there's a flow to the lab. What we're doing in here is we're training yeast to make human proteins.
Okay.
And then we're figuring out how to harvest those proteins and purify them and do that at scale and efficiently. So getting, it's a very expensive process to run. So the more lactoferrin the yeast can produce, we bring the cost down of the ingredient and make it economical.
So Dan, why are we in this lab? Why does lactoferrin matter to us?
Lactoferrin.
What is it?
It's the NIH calls it the miracle molecule.
Okay.
It's one of the most multifunctional bioactives in the body, and there's been a huge body of research because it is a major component of breast milk and colostrum, and there's decades of research on bovine or cow colostrum and lactoferrin for different applications. And it just has a wide range of potential health benefits, and we're solving a major issue in the world, which is infant formula not being as healthy as actual breast milk. We know that rates
it's a huge issue.
Yeah, we know that rates of development of children and indices of disease go up with infant formula, and we're trying to make infant formula more similar to human breast milk, and one of the key unlocks was having a human lactoferrin. Huge innovation, wasn't possible before. I liken it to the discovery of insulin. And this, we're on the forefront of something major.
That's huge. And it helps with your own body's production of stem cells, right?
Yes, so lactoferrin does four things. We call it the core four generally. So one, it helps with iron regulation, very complex. It helps as an immune modulator, so it helps regulate the immune response. You don't have that overreaction, you don't have that systemic inflammation, it calms it down. It also triggers stem cells, so we know that it can turn on gut cells, it can turn on skin cells, hair, muscle, neurons. It's in our brains, so very important there. And the last is it's antimicrobial, so it's going to have a huge influence on your microbiome, not only your gut, but also your skin and scalp, and it's a regulatory agent there.
So our body naturally makes it, especially as women.
Yes.
But as we age, does it decline?
It does, yes. Okay. There's a direct link for women, and it's men too, it's very important for men. But for women, it's called the estrogen lactoferrin axis. Estrogen levels actually trigger transcription of lactoferrin. So as your estrogen levels go down during menopause, your lactoferrin levels go down. And our belief, and we're studying this, is that some of the symptoms during menopause can be mitigated by resupplementing this human form of lactoferrin to address things like bone density, vasomotor symptoms, hot flashes, occurrence of UTI, vaginal health overall, and then fatigue and some of those other cognitive issues that can pop up.
Okay, well, I'll look forward to those studies. That sounds very promising.
Yeah, so absolutely. So we'll walk you through how we do it and what each of these groups are doing and how it works.
All right, let's go.
Cool.
Welcome to the strain engineering side of Helaina. So what we do here is we have all of our different genetic programs that we want to put into the yeast cells to try and increase the fitness to produce more lactoferrin. And what we do here is we kind of cut and paste different genetic programs together, similar to kind of like the old school movies with the cutting room floor. You'd have all these different pieces of film. You pick each different strip based on what you want to put together, and we put those together. We do that in thousands of different permutations, and we use those to then put into our yeast cells through a small electrical shock, and then ends up giving it the DNA that we're looking to express. And we do that thousands and thousands of times. And then, as you'll see later, we'll move down through the screening process and be able to select those winners that we ended up building on this side of the lab.
Okay, so we're looking for winners today.
Yes. The beauty of biology is it is kind of such a complex web. People think of things as kind of an on and off light switch. In genetics and biology works much more like a dimmer switch.
Yeah.
So when we start to make different changes to the yeast cells, the problems that we have to solve after the 20th change could be different than the problem that we were trying to solve with the second or third change. So it really keeps us on our toes, and we have to constantly keep being innovative with our designs to make sure that we're tackling the next problem we don't actually see coming down the line. So yeah, if you want to end up seeing what one of these looks like in the end, it's got a little bit of condensation on it. So this is the step after we have those plates that we grow them up, but then we need to grow them so we can get what we call single cells, so they can grow their individual colonies and be able to, each one of these is expressing a little differently than the other one. And so this is a giant quadrant plate that we're able to take each well, plate it into each region. As you can see in the fridge, we have many, many, many of these plates. And so this is what we then take and grow into another set of plates that we can test. So,
nice.
Yeah. We have here our biological safety cabinet. This is our sterile environment. And it's actually down there. That's our big electric chair. We have...
Where you shock them?
Yes, we shock them. We give them a nice little electric shock, and it comes in these strip plates of metal. And when you do this electric shock, it allows for a second the yeast, because yeast, different than bacteria, actually have a cell wall, not just a plasma membrane.
Yeah.
So you need to make sure you can get it in there, and this electrical shock is going to help them take that up. So this is where all of that happens.
Oh,
Yep.
interesting.
After the cells take up the different genetic information, we want to recover them and grow them. So these are the plates we're talking about. You get 96 different wells with each one having a different strain in it.
Okay.
And we have hundreds and hundreds and hundreds of these. This is deep well plate 1,238.
Oh, wow.
How
Okay.
many strains do you think we've done?
Over 10,000 easy.
Okay.
Yeah.
So out of that 10,000, we have one winner.
One winner.
Right
Yes.
now.
Right now we have one ultimate winner. Yes.
Okay.
We do these hundreds to thousands at a time. We pick a winner and then we build off of that winner. But, then we catalog and use for other information the previous winners. But at the end of the day, there's just one.
So, from the time that this company Helaina started to where we are now, we would say that your lactoferrin is more effective than it was in the beginning, or
it's I don't know. You can.
Yeah.
answer
How
that.
does that
it's,
work?
It's not that it's more effective. What we're trying to do is make cells that don't normally make lactoferrin make more of it.
Okay.
And the big job we have to have, which is on the other side of the lab with our analytics, is to make sure that every time we make a new strain that makes more lactoferrin, that we can prove that it is identical to the lactoferrin we were just making.
I see. Okay.
So it's more about just making enough that we can get it to everybody and make it cost effective versus making a different kind of lactoferrin.
I see. Okay.
Yeah.
So you're trying to mimic the same one, but do it in a more efficient way.
Yes.
So that everyone can have it.
Yes.
100%.
Yeah,
Our goal is every baby and adult in the world has access to this protein. So all this work is to lower the cost of the material so that we can make that happen.
Okay.
Because getting these yeast cells to make this complex human glycoprotein is not easy.
Yeah.
And it might not always play well, so we have to make sure that we are working with the cell, listening to it, and making it better and better so that it wants to make more of this and remains healthy.
Yeah, you're the cell whisperer.
Exactly. Yeah.
Okay. This is cool.
So this is the ultimate workhorse on the DNA and strain side and high throughput screening side. This is called a Hamilton Vantage. This is a large lab liquid handler. And this is so that it does two major things for us. It does high throughput screening of moving different liquids from one container to another. And one of the other big kickers is the traceability of each one of those movements. So the human hand, you're going to work through something, you can make mistakes, everybody tries to focus, but this, we give it a very specific list in the computer.
Okay.
It knows exactly where it's going to take something from point A to point B with a specific volume. And that way we can trust the different movements and we can keep track of thousands and thousands of liquid changes throughout the day.
How do you incorporate AI technology to make this more effective?
I mean, right now, one of the biggest things is us trying to leverage the different metabolic pathways as far as a design approach. We can only rationally design so much, but it is one of those things where it's, the user is able to use the tools to make the decisions. And AI has really helped us be able to map cells in a way that we couldn't on a whiteboard, right? There's so many different interactions, there's so much data in these databases, so we can use AI to leverage that and say, hey, because some of the things we're working on in these cells, nobody's ever done for this specific situation. So you never know what the outcome might be on the other side. So if we can use AI to leverage all these different pathways to give us kind of a good direction of what the outcome might be, what's an area we might want to look at, or what's an area that maybe isn't worth our time that maybe we thought was important.
Okay.
And so that's one of the ways, at least on the design side, that we've been leveraging AI to figure out what our next strategy is.
Yeah, what areas you're going to explore next.
Yeah.
Okay, that's cool.
So yeah, this is our fermentation lab, so where we run sort of the scaled down version of our manufacturing process. So these are bioreactors, and they essentially have all the same controls, inputs, and outputs, I guess, that they would have at manufacturing scale. So it allows us to mimic our manufacturing process here in-house and develop our process further to make more and better protein. So you can see that they're kind of like a beige opaque color. So that's because these are at the end of the fermentation cycle. So they're filled with yeast, and they're also filled with lactoferrin. As I said, we can like sort of control everything about these reactors, and we can also monitor them as they're running and respond to trends that we see happening during the fermentation. We have 16 reactors, and we use them for, number one, strain screening. So early stage, or the strain engineering team will develop new strains of yeast that are better at making protein. And so we then test them here in a manufacturing-like environment to validate those new strains. So that's one of the big things that we do here. So that's actually these 6 reactors over here are all running different strains that we're evaluating the performance of.
So exciting.
Once we do that, over here, we do further extraction. So we take that broth, we filter it, and then this is actually a gas chromatography machine. So we run the broth through here, and all the lactoferrin sticks to this column.
Okay.
We take that, and then this is actually a spray dryer that we have, a bench scale spray dryer. I've never seen this before coming to Helaina, where we can make raw powder, which would be the finished product, and it turns into, from that broth, from the strain, we get this, and this is the actual finished product of Afera, called pink gold. So this is pure lactoferrin.
Pink gold.
Yes, and the iron gives it that pink color, so there's a little amount of iron in the
So you
lactoferrin.
mentioned in the beginning that like 350 milligrams is like a
340.
340 milligrams is like the perfect dose that you would say. So how much of that, so you can show the...
So 340 milligrams, that's a good question. It's probably about the edge of my pinky finger there.
Okay, so it's not much.
Not much at all. Very small amount, goes a very long way.
Yeah.
Or 2 of our capsules.
2 of your capsules.
Is 340 milligrams.
So that's what you did. You did exactly.
Yep.
Okay.
And I have to give Michael credit because most brands are dosing at a lower dose, still efficacious. Michael's the only one in the world that has a 340 milligram dose. So let's go to our most expensive piece of equipment.
Okay.
And this is how we verify at a very, under a very high frequency picture that our lactoferrin is always the same.
So this is the analytics room where we perform a bunch of physicochemical characterizations. And why we perform these characterizations is to ensure that the product that's being made conforms to what we know about the protein, and that we ensure consistency from batch to batch and as the strain progresses. When we enter into times of scaled up production, we want to make sure that what we produce is in fact the right thing. And one of the analytical techniques we use is mass spectrometry. We utilize this instrument here, which is a high resolution, high mass accuracy, QTOF type mass spectrometer. And that's a lot of words, but essentially what it means, it's like a scale. And it's a scale that can weigh really, really small things such as molecules. And how we do it is that we take a molecule and we make it into an ion, and then we send it flying down this tube here. And how fast it flies is dependent on how heavy it is. So the way that we utilize this strategy is to say, we can take the intact protein, we can take lactoferrin and measure the mass of it. And we know that lactoferrin should weigh 76,132 Daltons. It always has that mass. And we confirm that what we produce, in fact, also has that mass. Then we can start getting a little creative. We can take the protein and break it up, and we can look at which decorations sit on the protein backbone and where do they sit. Do they sit in the same places as we would expect them, as we have seen in the naturally occurring protein, and to the same degree as we would expect? We can then get even more creative and break things more down and look at the individual amino acids and at the small metabolites to see how is the cell system actually doing. And we do all of this to, our CTO has this analogy. He likes to say, if it quacks like a duck, if it walks like a duck, and it has feathers like a duck, it's probably a duck. And that's basically what we check here. We check that all the physicochemical parameters are within spec and that they are correct. It's a very fun machine, and we can measure so many different things with it.
Yeah, so there's tons of fun things that we can do.
Oh my
with
gosh,
this
this is very exciting. I need one of these.
Yeah.
Where do I buy it?
I wish it had more moving parts that I could show for the camera, but unfortunately, this
No, you
is just what it
explained
looks
very
like.
well. Thank you.
Cool. So that pretty much.
This was amazing.
that's
That
all.
was
Good.
perfect.
Okay, I
Yeah.
don't know if it's
No,
too
it was
technical.
perfect.
Okay.
No,
cool.
my audience loves this kind of stuff, so
Perfect.
it'll be great.